see if I can do this with both hands, sorry. Welcome everybody, welcome to the summer school. My name is Versluis. I'm Principal System Engineer at QuTech in Delft. QuTech is a collaboration between TNO, which is our national research laboratory, similar to, for instance, Fraunhofer in Germany or CNRS here in France. And TU Delft, of course, the Technical University in Delft. A lot of the slides that I'll show today are not my own. I asked a number of colleagues to also help with providing me some input for this first talk of today. And I want to first start with telling you a little bit about myself. So I graduated in 1996, a long time ago. Did a master also in applied physics in Twente. And at that time I also was very interested in computer science. So I did something which would now be like a second master or a second bachelor. I don't know exactly the amount it counts to, but in computer science. And today I'm still grabbing the fruits of that because in quantum computing technology you have to combine, of course, both physics and computer science in one. After my studies, indeed, I went to the US for a couple of years as a visiting researcher to Lawrence Berkeley Lab. And I would really recommend everybody, not only summer schools like this, but if you have the opportunity to go abroad, either during your studies or afterwards, do it. It's a great experience. So if you get the chance, or you either take the chance or you make the chance, do it. I'm Principal System Engineer at TNO, but I have a couple of roles. One of the roles is indeed I'm leading the Catalyst 1 program on quantum computing, part of the National Growth Fund in the Netherlands. That's a 50 million euro program where the goal is to develop quantum computers, prototypes of quantum computers, to deliver some kind of quantum advantage by the year 2028. There's a lot of debate, obviously, about what quantum advantage is. For me, I usually define it as quantum computers that can deliver some kind of economical value to the users. So not necessarily better than normal computers or faster than normal computers, but if you give some kind of edge to computing using quantum computers, that's already advantageous for society. So it can be that you do something using less power, for instance, if you compare it with computing with supercomputers, or doing something differently. If you calculate something in a totally different way, that could also yield new results or new insights. In 2020, we started the national program by launching indeed Quantum Inspire. And Quantum Inspire is a cloud computing system where we have two physical quantum computers connected to the cloud, one based on electron spin qubits. Unfortunately, we had to take it online 1 year ago because it had too many thermal cycles, so the chip died, unfortunately. And we were not yet ready yet with tuning up the new device, but we can hopefully have that online by the end of this year. This has 6 qubits, and we have a system with superconducting qubits connected to it. Only 5, but we are a research lab. We're not IBM or Google, who have the power to make systems with hundreds of qubits. And we're also connecting a system from University of Eindhoven, which has Rydberg neutral atoms as a backend. I would also like to know a little bit about you. It's not completely the same, but I hope everybody's going to get awake a little bit using this talk. But I want to do it a little bit interactively, so I'm not going to ask everybody who are you, what are you doing, but I want to like see some hands. So who has a physics background here? Most of you, and who has something else like math or still quite a lot. Anything not physics or not math? And what is that? Engineering, okay. Computer science, yeah, obviously. Anything else still? Chemistry, that's nice. Okay, so as you see already, quantum is not only about physics, right? It's about a lot of different disciplines that you need to build quantum computers or quantum sensors or quantum communication systems. You already see that here with the people here. But I would also like to take the opportunity to get a little bit of interaction between the people, because you have to spend the whole week here together. So hopefully you'll get to know each other a little bit better during the week. But I'd also like to ask you, spend 1 minute, talk with the person next to you. Not too loud, because we are a big group. Ask who they are, what they do, and try to do it like 30 seconds on one person and then 30 seconds to the other person, so you get to know each other. Okay, go ahead. That's great to see. I hope people can stop talking now. No, but thanks. I hope everybody had a little bit of time to get to know each other. I want you to understand also that this is important, right? If you want to meet people and ask people questions, etc., first take some time to get to know each other, even if it's just a minute. It will break the ice, and you'll see during the day and during the week it will be much easier to talk with each other and ask questions. And also here, if you want to ask me questions or anybody else, just raise your hand and go ahead. A little bit about the program for me for today. So I split the talk into a couple of different sections. I hope I can make it within all the time slots that I thought would be appropriate for these talks. But I'll start with a basic introduction, a little bit to get everybody on the same page. Some people have maybe a very good background on quantum, some others maybe have a little bit less background, so just a little bit of history and a little bit of introduction. Then I'm going to tell you a little bit about different applications of quantum technology. So it's not only quantum computing, but also other technologies. I have a background in quantum computing, but I'll tell you a little bit about the other applications as well. Then something differently, maybe for the physics student, not for the engineering students maybe, but I'm going to tell you a little bit about systems engineering. Not only because I'm a system engineer, I find it interesting, but also because I think it can be important for you, for your own career, but also your own development steps, whether you're going to a company, whether you're going to do a PhD position or become a postdoc or whatever. I think these kind of skills can help you in developing your own skill set and doing the work that you need to do. Then after the break, I'm going to tell a little bit about quantum computing, so focusing more on quantum computing itself, and then going to apply together with you system engineering skills and methodologies on quantum computers. Will not be fully deep dive, but just a little bit on the surface, but to give you a little bit of feeling what it means and how you can apply these skills to quantum computing. And then we'll have a little bit of discussion at the end to see how this all went. So a little bit about the basics of quantum computing, quantum mechanics. I want to make a distinction between a couple of different things. So quantum mechanics is really about of course, the math and the formulas and the physics. So understanding the laws of physics that govern a couple of phenomena that we see. Quantum devices usually are referred to really small items like quantum chips or quantum communication nodes, quantum sensors, etc. So devices containing actual quantum mechanical systems where you make use of the quantum mechanical properties. And then quantum systems can be much larger, right? So a quantum communication network consists not only of nodes that generate entanglement or that measure quantum states, but they also consist of a lot of classical hardware. You need to have classical communications between the systems. You need to do signal processing, all that kind of stuff. So they're usually referred to as quantum systems, although the quantum part may be just a very small part of it. So quantum, of course, is not new, right? We saw already in the presentation from Martin that in Leiden, Honors already, I don't know if I didn't discover, of course, low temperatures, but at least he worked with it quite a lot. But the first revolution on quantum mechanics was more about how to use quantum. So for instance, lasers use quantum mechanical phenomenon, but you don't really need to understand how it works in order to use it. People develop lasers and they say, oh, this is a neat thing, and you have coherent light. But you don't need to fully understand it in order to use it. Now we are in the second quantum revolution, where we see that quantum mechanical properties can be used in many different systems, and you can do a lot of different stuff with it. But you really need to understand how it works in order to use it. And I'll give a little bit of examples of that a little bit later. So already more than 100 years ago, it started with quantum mechanics. but it was more about trying to explain certain phenomena that they were not able to explain with the classical physics that they had at hand right now. So people started doing measurements where they saw all kinds of phenomena which they could only explain by assuming that there was a quantized form of energy, for instance. And people like Thomson and Rutherford, all these experiments, and Planck was one of the first people who actually tried to explain the phenomena and used quantized energy levels in order to explain that. And also, of course, Einstein had a famous paper where he applied energy quantization in order to explain the photoelectric effect. But it was all like explaining the things that they saw. And it took a couple of years until the 30s of the last century for people to develop really a framework, and a theoretical framework on what is quantum mechanics, a little bit more than just explaining the experiments. And after that, so most of the groundwork was already laid in the 30s and was expanded on a little bit later. But during the centuries after that, not a lot of things happened anymore. So there was still, of course, a lot of research in quantum mechanics, but the mathematical framework was already developed, but it took some time for the first, let's say, actual applications to being developed. And it also took some time before people started to accept that quantum mechanics was really there. So everybody, well, not everybody, I think a lot of people have heard about the EPR paradox, where Einstein and Podolsky and Rosen wrote down this paradox and said, well, is there really quantum mechanics present? Meaning that, for instance, there's non-locality between systems that's really there. So two particles can be in a superposition, but they can be at a large distance, for instance, or they can be entangled and they can be at a large distance. Or is there some kind of hidden property, hidden variables that we cannot see and cannot understand yet that actually explains these phenomena? And it took another 30 years, so until 1964, until Bell's theorem was written down, where there was a theory explaining how you could do a measurement in order to prove or disapprove whether hidden variables were used or not. And it took another couple of years. I think it was around the time that Harosh and, no, it was Aspect, Clauser and Zeilinger that got actually Nobel Prize for it, but I don't know exactly when they did the experiments, to actually show that hidden variables were not used in quantum mechanics. And it's actually quantum mechanical non-locality does exist. So in quantum mechanics, there's a couple of characteristics, of course, that most of you have heard of that are really different from classical mechanics. So it starts with the wave-particle duality and also superposition. So particles can be not only a particle, but they can also be a wave. And some things can be well explained with assuming that they are particles, but for some other phenomena, it's much better to assume that they are waves. I think the wave theory is the most practical one. So try to think in waves, that helps you a lot. And also the quantization of properties, of course, that's where quantum mechanics is coming from. That a couple of properties like energy and momentum and a lot of other properties are quantized. So they only come in small packets. Oh, sorry. And of course, there's more, even strange phenomena like quantum tunneling, where you see an illustration here from Wikipedia. If you have normal classical particles, they cannot have an energy, of course, a negative kinetic energy. That would be strange. But in quantum mechanics, that's possible. So you can have particles that enter a forbidden region where they have negative kinetic energy. And it actually means that they're tunneling through a barrier, for instance. So those are phenomena that are possible in quantum mechanics, but they're not possible in classical mechanics. I'll also give you an example on how that actually used in quantum dots, for instance. So I think I don't have to explain here a lot, but everybody knows these nice experiments where you can have interference between particles. Not only multiple particles, but also single particle interference exists. So a single particle can enter through these slits and interfere with itself and generate these interference patterns after the diaphragm. I'm not going to do a lot of math. First of all, I don't have a quantum mechanical background, so I'm not going to spoil you with some things that I don't know. But the evolution of quantum systems is described by a very neat equation, the Schrödinger equation. And it really helps if you understand these equations and can use it. So if you are going to deep dive into quantum mechanics, try to get a grasp of it because it's really helpful. And it's actually describing the evolution of quantum systems based on the Hamiltonian. The Hamiltonian, you can determine them with the kinetic energy and the potential energy, and you can apply it to single particles, to multiple particles, and actually describe the full quantum state of systems. This one already told, but here's an example of tunneling. Here you see one of our own chips, which has two quantum dots in it, where we try to capture single electrons. And we use quantum tunneling in order to have interaction between the dot on the left side and the dot on the right side. And that's how we create entanglement between the systems. And of course, finally, one of the other aspects is uncertainty. So Heisenberg's uncertainty principle, which tells you that there's a fundamental limit on what you can measure actually and which properties you can measure at the same time. So some properties in quantum mechanics are commuting, so you can measure them separately, but some others are not commuting. But there's also this Heisenberg uncertainty principle, which tells you that you cannot measure two properties with the same accuracy at the same time. And finally, measurement collapse. Personally, I find this still one of the strangest properties of quantum mechanics. But you can show that properties, measurable physical properties like momentum or energy, you can actually describe that with a mathematical property, the Hermitian operators. And these Hermitian operators, they always correspond with some kind of observable. And when you apply the operator to the state of the system, you get the properties, you get the probabilities that you measure certain eigenvalues of the quantum mechanical system. And actually, after that, when you do the measurement, the system is either in one of the multiple states that the system can be in, one of the eigenstates. People still don't understand how this actually works, but it's there, and when you apply it, you just apply the math, it works quite well. Let's go to the qubit. Who has familiarity or knows about two-level quantum mechanical states? Lots of them, that's easy, yeah. So I'm going to describe the qubit again a little bit, but I'll do it then a little bit faster, because this is the main property that we use in quantum computers, the qubit. And it's actually a two-level system, of course, with two different states, usually a ground state of a system, for instance, the ground state of an electron, or the ground state of an atom, or the ground state of a mechanical oscillator, and another state, an excited state, that you use to define the two properties of a bit, a 0 and a 1. And the system can, of course, be in a superposition, as you all know, and we usually describe a qubit on the Bloch sphere, where we map the complex state onto, let's say, a physical state with two different angles that describe the position on the Bloch sphere. What I want to emphasize is that often you hear that qubits can be in two different states at the same time. Saying, well, it can be in a 0 state and can be in a 1 state, can be in those two states at the same time. You always hear this example where you have a cat, it can be a living cat and a dead cat. Here I also want to emphasize that superposition states are just a mathematical construct defining one state as a function of two other states. So for instance, if you take these two states, a 0 and a 1 state, as your starting states, as your basis states, you can describe any other state, like a state here on the equator, as a function of those two states, but also vice versa. You can take, for instance, this state and this state as your basis state, and that state would then not be a superposition, but this state or this state would be a superposition. So it depends on your basis states, which states are superpositions. But there's always an obvious choice to take. For instance, for electron spin qubits, like these ones, we put them in a magnetic field, and then these states are the eigenstates of that system. So it's obviously the best choice to take those states as a basis states. But I do want to remember everybody that superpositions are not like two states at the same time. It's still one state. In quantum computing, quantum decoherence is a shitty thing. Because quantum decoherence is the loss of quantum coherence. So when you define a qubit state, it's only defined well if you have a good phase relationship between the two basis states that form the system. But if you have an interaction between your qubit and the environment, you can lose part of your information in your system. So it can, for instance, be thermal relaxation, where one of the states when the system is slowly going, for instance, to the ground state. But it can also be dephasing of your qubit, where you lose phase information. And there are ways to compensate decoherence, but there are so many different types of decoherence that it's very difficult to compensate for every type of loss of information. And the simple reality is that we're not sure yet if we can cope with all kinds of decoherence effects. We try to cope with them, but we cannot cope with all of the effects. And here you see an example, which is a little bit of an old list, but it shows here on the left side different types of qubits. And here the coherence time, roughly the coherence time of these different types of qubits. And it also shows you the amount of time that you roughly need to do an operation on the qubits. And if you divide these numbers, you can see how many operations you can do with different types of qubits. So it's a little bit of outdated, so maybe some numbers are more positive and some others are maybe a little bit more negative. But it shows you that the range of operations that you can do on qubits is not that large. If you look at normal computers, you do trillions of operations on them to do a computation. And here, for some types, you may be lucky if you can do like 1,000 operations or 10,000 operations within the coherence time. So you'll need something to fight decoherence. Otherwise, it will be almost impossible to do a good calculation of your system. But you do not need only superposition. So if you have a quantum computer where you can generate only superposition states, then it's useless. You cannot do any quantum computation if you only have superposition. So quantum entanglement is really the resource that you need to do quantum computing. And I'll show you in some other applications that's not only the resource for quantum computing, but it's also the resource for quantum sensing and for quantum communication. So please remember that entanglement is the crucial source. It's not superposition. Superposition is not special. It's strange, but it's not special. Entanglement is really special. And the concept of entanglement doesn't have a classical, let's say, counterpart, of course. So we don't have anything in classical mechanics that behaves like quantum mechanical entangled systems. If you want to compare it, there are things like this. You can compare it, for instance, with two coins which are glued together. So if you flip a coin, you have a probability that you measure heads or tails. If you have an entangled system, it's like they're connected to each other, even if they're very far apart. And if you flip the coins, you have a certain type of probability that you measure 0 or 1. But for entangled systems, these are correlated. And with normal systems, of course, if you have two separate coins, it's never correlated. And this is a special kind of correlation that doesn't exist in quantum mechanics. It doesn't exist in classical mechanics. And here's an example of this. When you have two different separate qubits which are not entangled, you have like a 25% chance that you measure either a 0-0 state or 0-1, 1-1, or a 1-0 state. But if you have entangled states, you can have other kinds of probabilities for measuring the systems, like, for instance, this Bell state, where you have a 50% chance of measuring a 0-1 or a 1-0 state. I told you already a little bit about the EPR paradox, and Bell's theorem in 1964 was made up by Bell and actually showed mathematically that there's that this correlation actually exists, or it doesn't show that it exists, but there are methods to show that it exists. And it was shown later by actual measurements a couple of times again that these entanglement effects actually exist, and we make use of them every day in our quantum computers. I'm going to skip this a little bit because of time, but I want to focus on the last part because that's important for my work, and maybe it's important also for the experiments that you're going to do. You can only access the information encapsulated in a quantum state via quantum measurement mediated by an observable. I'm going to repeat it again, not the whole sentence, but it means that some properties you cannot measure directly. You just have to measure the observable, and there's a chance that you measure one of the different eigenstates of the system, but if you want to capture all the potential eigenstates of the system, you have to collect a lot of data. If, for instance, you bring your quantum computing system, your qubit, in a superposition state, and it's very close to the 0 state, and it's very far away from the 1 state, but you actually want to measure the probability. What are the actual probabilities? You have to repeat the experiments thousands of times, or sometimes tens of thousands of times, in order to collect data. So measuring quantum properties can take a lot of time. That's why they have a lot of PhD students. It's not because they like the education, they just need the PhD students, so that's a secret. So, summarizing, basics of quantum, everybody knows this, but I just want to keep focus on it. So, quantization effects, the wave-particle duality is an important factor to take into account. Superposition and collapse, the uncertainty principle, I haven't talked about it here. We don't need it in quantum computing, but could be in other parts where you need these kind of things. And entanglement, which is the resource for quantum computers and quantum communication. I think I'm doing quite well, yeah. So a little bit about different applications of quantum technology. Like I said, we have the first revolution, as they call it, where people started using quantum mechanical effects to build stuff like transistors or lasers. And we're now in the second quantum revolution, where we're really harnessing quantum coherence and quantum effects like quantum entanglement to actually, use it as a really valuable resource. And like I said, quantum coherence is really about keeping track of the phase. So if you have a superposition state, for instance, the phase becomes really important. And you see that, for instance, here. Here you have a representation of an algorithm, Shor's algorithm, or a little part of Shor's algorithm, which is used to do decryption of classical codes. And here you see entanglement operations between the different qubits, and the entanglement operations really take into account the effect of the phase difference between the different qubits, but also the phase difference between the different states in qubits. So it's really important that you keep track of this phase and you control this phase and control the quantum coherence. Also the difference between the first revolution and the second revolution. So you do not need to understand this, understand what a qubit is and what phase is, etc., to make a transistor. Sometimes you need to know a little bit about tunneling effects because the transistors become smaller and smaller. So that means that sometimes electrons already start to leak out of the dots and interact with other electrons on the other side. So you need to understand a little bit of that, but you don't actually need it to design transistors or design lasers. But if you design a quantum computer, you really need to understand these kind of effects. And why is quantum coherence important? There's a whole range of different problems that we want to solve with computers, with normal computers, your laptop or supercomputers. And there are easy problems to solve, and there are difficult problems to solve, and there are problems which are virtually impossible to solve. And for instance, the simple problems like matrix multiplication or index search, etc., those are relatively easy. Then there are things like prime factorization and finding the best root in the graph, which everybody knows they are very difficult to solve, and sometimes you can only find, let's say, a value which is close to the actual value. But there are some problems, like, well, it's a negative problem, but doing factorization in order to decrypt a code, for instance, like the RSA encryption code, that is really an NP-hard problem. So which means that it can take millions of years on a normal computer in order to do these calculations. But if you have quantum coherence, oh, it's not on this slide, it comes a little bit later, but if you have quantum coherent properties, then actually you can solve some of these problems which are in this region. So you cannot solve all problems, but there are some problems that are easier to solve, and some problems which used to be exponential problems, so exponentially difficult to solve, they become polynomial problems. So they get a little bit easier to solve. Maybe not completely easy, but easier. So some practical issues. I said that for entangled systems, but also superposition systems, it's important that we keep track of the phase and control the phase. It's one thing to isolate a system. So you can put a system at really low temperatures, at millikelvin, dilution fridges. You can make all kinds of thermal protection around it. You can isolate it from all kinds of mechanical vibrations, from your pumps, from your stages, etc., that move properties of your system. But you also want to interact with it, because otherwise it's useless. And in order to interact with it, you have to make some kind of channel to interact with it, either microwave excitations or thermal excitations, or you want to shine a laser on your qubits. So that means that you open up a channel for interaction with it, and that also means that you're opening up a system for decoherence. So this is the thing that we're always fighting when you try to make quantum mechanical systems, whether it's a quantum sensor or a quantum computer or a quantum communication system. You want to isolate it, but you also want to interact with it. And that's the balance where you need to find, let's say, the optimum solution to do that. And I want to give a couple of examples why entanglement is a resource and how you can use it. And this is a very generic picture. So if you have some kind of process and you want to generate an outcome, you need to have input and you need to have some kind of control on how that process works. This picture will come back later as well. But here you see how entanglement is a resource for different things. So I already showed the Shor's algorithm, where you need to generate entanglement between the qubits, because otherwise you cannot do any useful calculations. So these controlled rotations are entangling operations. But here's another example from a quantum communication system. Suppose you have two different nodes, one here in Strasbourg and the other one in Dortmund, for instance. And you want to communicate between those two locations, and you want to use quantum mechanics to enable communication between those two locations. You can do things like entanglement swapping. So what you can do is you can generate an entangled state here, and you can generate an entangled state there. And there's a third party in between over here, which can be like a satellite communication system. And each of these parties, they send one of their qubits. So if it's a satellite, it will be a photon. They send one of the photons to the intermediate channel at the top, where they do operations like a measurement on the different states of the qubits. So usually there are Bell states over here, a Bell state over there, and they do a Bell state measurement over there. And by doing the Bell state measurement at this location, you generate entanglement between locations A and B. And if you have entanglement between locations A and B, you can do some kind of quantum communications between location A and B. For instance, do exchange of quantum keys. So this is one way where you see that also here entanglement is a resource to do something practical. And you can classify applications in different ways, but here I show one way of classifying applications, and also want to show how they can come together maybe in the future. So not immediately. I don't think it's useful to try and do everything together at the same time, but there is some links between them. So long distance entanglement applications are for quantum communication. If you want to communicate over short distance, that's not always useful to do to use quantum entanglement. If you want to communicate over large distances and you want to do it safely, you'll need entanglement. You need short distance entanglement between different qubits on your chip, for instance, to do computing. And you need short distance entanglement to do quantum sensing. For instance, you generate an entangled photon. You send one photon to a sample that you want to measure. And with that, you can extract some kind of information from your sample that you want to measure and use quantum mechanical information from it. But it's also possible, for instance, to connect quantum sensors through a quantum communication network to a quantum computer elsewhere. I think this is all far future, but things are going very fast. So there are thoughts already about connecting quantum sensors, quantum communication systems, and quantum computers or normal computers together in order to send quantum information from one location to the other location and process it there. So I'll give a few of these examples later. And of course, with quantum computers, you can do all kinds of different quantum computations. So a little bit in short what these different applications are. So quantum communication and quantum internet is basically a network that has both classical channels. So please don't forget this, you always need classical channels in order to do quantum communication. It's not possible to just make only quantum communication channels between different locations. You also always need some kind of classical communication between channels. With the goal of distributing entanglement between those nodes. That's actually what a quantum communication network is. It's just distributing entanglement and using that. Quantum key distribution is one nice example of quantum communication. This is a recipe to transform this long-distance entanglement into a classical bit string that you can then use to encode normal classical information. So you use quantum to generate a bit string, which is classical, and then you do classical communication between those nodes. You're not doing quantum communication between those nodes. You're using entanglement to generate a bit string, which is safe. You know that nobody listened in on how this key was generated, and you use that key to do normal communication. If somebody breaks your key, then this was useless. So also you still have to protect your classical communication in some way, that you do not send your key, for instance, over the same classical channel or another channel that people can break it. If you want to know more about QKD, for all of these things, Google QKD, do some YouTubing, and you'll see exactly how this works, where people, Alice and Bob, generate entanglement in different bases and then measure them. And just by communicating between them on a classical channel, they can still make sure that they can generate a safe key. These are measurements that have already also been done. It's possible, for instance, to use quantum mechanics to make better interference measurements between photons that arrive, for instance, from a star or from deep space, and to locate where actually the photons are coming from. Here they use, for instance, squeezed states, where they share also entanglement between different locations. And this is a method to optimize, let's say, the measurements that they do classically. They make it already a little bit better. So with entanglement, you can make classical measurements better. Usually, you have a little bit more accuracy than compared with just classical photons. I do not know too much about this, but maybe somebody else does. You can ask somebody else. But it's also possible to make clocks synchronize better that we can do with regular atomic clocks using quantum entanglement between those clocks. And like I said, there's also the application of universal quantum computing, where you can make a system that uses entanglement to do computations. And here you need a couple of different things, and I highlighted this one, which is often mentioned in quantum computers, the Vinci criteria, where you need a couple of things to do quantum computing. You need a qubit. You need to be able to initialize the qubit to a certain state, because you need some kind of input state to do a computation. You need long decoherence times, because you don't want to lose the phase information in your qubits. And you need a set of gates, a set of operations on these qubits to do a computation. And this needs to be a universal set, so you're able to do any computation that you would like to do. And you need to be able to measure them. Also come back to these criteria a little bit later, because you can, if you're a system engineer or an engineer, you can read these as requirements of your system. It's the basic requirements of your system, not really well formulated, but they are requirements for your system. And there are over 20, maybe even by now more implementations of universal quantum computing. You can use photons, you can use electrons, you can use annealing, you can use gated circuit systems, like a quantum gate array-based system where you can do these kind of calculations. But you can use all kinds of more exotic qubits, like Majorana fermions, where you can do a different type of computation that's less sensitive to external noise than, for instance, these gate array-based computing systems. Is it possible to do quantum computations with qubits that are noisy? Yes, it is, but it's not that useful. So it's possible to do variational quantum algorithms, for instance, in quantum chemistry, where you do a part of your calculation with a quantum computer. You measure the result, it's not optimal. You compare it with the expected output. You do an optimization of your quantum algorithm and you run the circuit again. And you repeat this a couple of times, and this way you can measure properties, or you can simulate properties that are not simulatable with a classical computer in principle. But you'll need lots of qubits in order to do something useful. But it's already been shown that you can do calculations like modeling the ground state of simple molecules, for instance, with a quantum computer. So it has been done, but a lot of it is, there's a lot of improvement needed on the coherence time of qubits in order to do something more useful. And in general, if you want to do things that are more useful, like running different types of algorithms, like Shor's algorithm, or doing complex chemical simulations, or astrophysical simulations and cosmological simulations, you'll need a lot more qubits, and you need more stable qubits, and you will need something like error correction on your qubits. And finally, there's another example of quantum computing, basically done by D-Wave. Probably a couple of people have heard about this Canadian company, where they use quantum annealing to do quantum computations, which is a different type of quantum computing, where you use an Ising model that is close to your physical model, but it's not using actually operations on qubits to compute. It's more like you put your system in a state that resembles the physical system that you want to simulate. You let it run for a while, you let it anneal to the ground state, and then you hope that the ground state is similar to the ground state of the system that you want to simulate. And quantum sensing, last application, you have many different quantum sensors available already. So people might not know that, but there's many different types of quantum sensors that you can make, and there's already a lot of quantum sensors that are out there already available that you can actually buy. They work, they use quantum entanglement or superposition states, but they actually are there. And basically what a quantum sensor does, it takes some kind of input, it translates that to another signal that you can then read out, can be an electrical signal or an optical signal. And for instance, a couple of examples are these one. To measure gravity, you can measure gravity quite accurately using quantum sensors. And here you see actually results of a quantum gravity sensor that was used to map out different gravity anomalies, difficult word for me, in Mount Etna. And this is another example where you take a vapor and you illuminate this vapor, and photons are actually absorbed into these atoms. And then when these atoms have absorbed can absorb no more light, then the system becomes transparent. And then you use the fact that this quantum mechanical vapor is sensitive to magnetic fields. So what's actually a nuisance in quantum computers, that qubits are really sensitive to the external environment. So it's a bug in quantum computers, it's a feature in quantum sensors. So we actually use that it's very sensitive to these external magnetic fields. So you can measure when a small magnetic field from the outside is actually degenerating these vapors. And these are actually built and sold and used. So you have these quantum sensors, they're very sensitive, and you can measure you can use them, for instance, to measure properties of your brain. So you can measure differences in the magnetic field generated by your brain. It's very sensitive also to the outside magnetic field, so you have to use special chambers where you can do the experiments, so you have to shield it from other external factors, but they are already used. So on one hand, quantum is new, quantum communication systems, quantum computers, they're very early in their development, but quantum sensors are a little bit further ahead. I'll go on to a different topic. System engineering. So bear with me, this is totally different. It's not about quantum anymore. It's about something classical. I want to start with this picture. It already gives away something, but does anybody know what this is? No? Does anybody know the company? Do you know what the company does? No hands? Yeah. Yeah, they make lithography machines to make chips. They are one of the largest companies in the world, if not the largest company, and the only company that makes systems based on extreme ultraviolet radiation, where they make all the chips that are in your mobile phones, whether it's from Samsung or from Apple. Most of these chips are made by ASML machines. This is one of the first machines. I'm not sure if it's an EUV machine, I don't think so. But this was around 1990, 2000, when ASML started. And they started building the first prototypes of these machines. And I worked for ASML for a couple of years. And I started working on EUV machines in 2003. And they didn't look like that. They were a little bit more elaborated, a little bit better. But these are some clips from the news items from 2012, 2014. So already 10 years after these initial creations of EUV machines, stating things like EUV will never happen. It's impossible to align the lasers. It's too difficult. It's too much. EUV, will it work or not? People already spent billions of euros on EUV machines. Lithography is getting so complex that even the most brilliant minds, with all the resources that they have and the best tools, they are never able to make it and meet the deadlines. Issues with pellicles, which are actually the things that protect the dias. I forget the English word, but at least the pattern that you want to make on the chips. So this could be the killer problem for EUV. But in 2014, 2015, they went from that to that. And nowadays, already since 10 years, let's say they have a monopoly on these kind of things. And they sell hundreds of them. Well, not only EUV machines, but also other machines, but they sell tens of EUV machines per year for, I don't know what, 60 million or 100 million euros a piece. And they went from making 1 wafer a day to 100 wafers per hour. Why am I telling this? So this was the system 20, 30 years ago. And this is how quantum computers look today. So I hope you see the similarities, except from the people that are there. It's somebody else. But we're actually doing the same things in our labs, right? So we're pioneering quantum computers, we're pioneering quantum sensors, we're pioneering quantum communication systems, and some of these systems fail. So it could be that quantum computers will never work. It could be that quantum communication systems might never work, but we have quantum sensors already, and we know that quantum computers can work because we make some prototypes, and they still look like shit, maybe a little bit. They look like a lab is supposed to look like. But if you put a box around it, it really looks much better. And I hope that in a couple of years, 5, 10 years, with a lot of help, also from you people, we can go from these systems to these kind of systems that actually produce a lot of value and do quite neat stuff. I didn't tell you why system engineering is needed, but system engineering is actually, let's say, the profession that tries to deal with these complex systems. So how do you make something that's so complex that nobody is able to understand all of the parts of your system? Because that's virtually impossible. There's hundreds or thousands of people working on these machines every day, and they all work on different parts of the machine. And that's where system engineering comes in place. So I'm not going to read out what system engineering is here. You can read it by yourself. But it's actually like technical project management. So you try to make something that's really complex, and you do that basically by breaking it up. You break it up in small pieces that are manageable, that you know that work. And all of these pieces, of course, need to do their own little function. They need to perform, and they need to talk with each other, interface with each other, or you need to be able to put them together in the right way. So that's what system engineers do. They break up stuff, and they use all kinds of techniques to manage all that and put it back together again, and then verify and validate that it actually works. So system engineering is more like a profession. It's not something that you can easily learn. There's a couple of skills that you can learn in education, but a lot of it you learn by doing. You just start with small systems, and then you build a little bit larger systems, and then you build larger and larger systems, more complex. But you always use some kind of process. And you often hear things like a waterfall process. I have a picture, maybe a little bit here, where you start with what are the requirements and how does the design look like, and then you're going to make it, and then you're going to verify that it works, and then you maintain it, but it's usually not that simple. So this is really, let's say, the old-fashioned way of system engineering. You start with what you want to build, and you end with what you build, but you see that there's lots of iterations here. And you can work differently with these kinds of iterations. So you can have like a spiral kind of way, where you make some first requirements that are maybe not complete, and they're not fully accurate, but at least you have some requirements that you can work with. And you build a first prototype, and you implement it, you verify it, and then you understand, oh, okay, but we need to do this better, we need to do this better. So we need to formulate new requirements and make a new prototype. So that's a kind of kind of spiral way that you work with. You can also do it differently. You can also break up your system in smaller parts and do this for all the smaller parts. What you also see in software, for instance, a lot of times is that you do stuff really more like agile. You don't start with a full set of requirements, but you just take a little part of it and you just start working. You say, we don't know where we're going yet, but we know this. We start working with it, and then we learn, and then we see, okay, what's the next problem that we're going to tackle? So it still follows a process, but it's more agile. You just see what happens. And what makes a good system engineer, I think this is not only for system engineer, I think this holds for everybody. If you are in a technical study, in a beta study, either it's physics or math as well, computer science, it always helps if you have these skills. You'll need scientific thinking, so you really need to think like a scientist, or you have to be able to understand scientists, how they work, how they talk. They talk physics, they talk chemistry, they talk different languages, not physical languages, but they talk different languages, and you need to understand those. But you also be able to, let's say, take a step back sometimes. You say, okay, we're really working on these details, but taking a few steps back, why were we doing this in the first place? Because if you only think scientifically, there's always the chance of the rabbit hole. So you find something interesting, it's really interesting. No, it's not for a system engineer. It's not interesting, it's a bug. So maybe you need to solve it. You do not have to find it interesting. But you also need to think creatively. So sometimes there's a problem that you don't know how to solve. You must be able yourself or put other people in the same room, say, okay, we need to solve this. Put creative people there, put engineers there, put people with wild ideas in the same room and ask them, how do we solve this problem? So as a system engineer, it helps to have these different skills. Here I showed the V model. But I also want to explain a little bit more why this works and how it helps. Because what you see here is not only going from requirements and then making first architectures and build it and verify it. But you also see some important relationships, for instance, with the customer. So if you build a complex system for a client, actually, so could be another student where you make a system for, could be for yourself, or it could be that you work at a large company where you have to build a certain thing. You always have a verification. So you define requirements in the beginning, what does the system need to do? And at the end, you verify it with your customer. But also when you make an architecture, first architecture, and you build it, you verify, does it actually work? So you inspect it, and you test it, and you calibrate it. So these are all things that people already, I think a lot of you already do. If you make a technical system, you make a test setup, you do these kind of things. So you build something, and you verify, does it actually work? But you can do this better. I think if you work on technical systems and you make your own systems, try to think as a system engineer. What are the actual requirements? What I want to measure with this system? And do I actually am able to measure the things that I want to measure with these systems? Also, as a system engineer, you have things like opportunity and risk management. So when you make a system, you can think of, okay, can I use this system also for something else? Make it more valuable to use it for something else? Or am I incorporating something that's actually not useful for the system? Then maybe I should throw it away, not make it more complex. It's already complex enough. So there's a lot of risk management and opportunity measurement. As a system engineer, you spend quite some time on defining the requirements. So actually, what do I want my system? It can be a quantum computer, it can be a quantum sensor. What do I want it to actually do? And there's different types of requirements. There's things like functional requirements, what does it need to do? And there's performance requirements, like how well should it be doing this? And there's a tendency, especially in academia, sounds negative, but I don't mean it like this because I think that's the role of academia. But there's a tendency that people always say it should do it better than the previous version or as good as possible. I want to get the most sensitive system in the world. Okay, for yourself, think what is the most sensitive system in the world? Should it be 2 times better than something else? Should it be 10 times better? Should it be just a fraction better? And should it be better on everything? Or should it be one specific property like the bandwidth that needs to be increased? Or the sensitivity that needs to be increased? And what does it mean for the other properties that you want to measure? Is it okay if some other things get worse? Is that allowed or not? There's a tendency always to say, no, it should be better, better, better than the previous one. But think about, okay, what is the part that needs to be better? Then there's all kinds of design constraints that you need to take into account. Maybe some safety things if you're working with cryogenic equipment, for instance. Think about safety. And you can write down these requirements for yourself. It doesn't need to be a long list. So if you write down the requirements for a new Boeing or an ASML machines, I think there's hundreds of thousands of requirements that are listed. And if you go to the minor details of it, there's even more requirements. If you make your own setup, it can be 10 requirements or 20. But write them down. Exactly, what's the bandwidth that you want to achieve? What's the speed that you want to achieve? Writing it down helps you in your thinking process. And requirements have attributes. It's not just a number. It can also be like, how important is this? Do I need to finish this in the next year? Or is it okay at the end of my thesis that the system reaches these performance requirements? Or do I need some stuff right away? And how am I going to verify that it actually works? Do I know of a measurement that I can use to actually test whether it works? And if you think about that in advance, it can save you a lot of time later. And also, I've seen things go wrong at my own work, especially if you work with larger teams. If you work with 2 people or 3 people, then everybody knows what this means. The operational range shall be at least 2 times the signal bandwidth. But if you work with 10 people or 20 people, then maybe people have a different opinion on what bandwidth means or what operational range means. So also make sure that you agree on that. Maybe if you're doing research, little less important, but if you work at a company, it's really important that you have the same definitions. So this is a long list. I'm not going to go through all of these, but writing down good requirements is not easy, but it's important. You can think about, is it correct? Is it complete? Do I don't have 2 requirements in one requirement that are actually overlapping a little bit? Maybe I have requirements that are actually conflicting requirements. So on one hand, I want to do this. On the other hand, I want to do that. Okay, how am I going to solve this? Is it actually feasible to make these requirements? Can I test it? All these kind of things. So you can think a little bit about your requirements. This sounds maybe even boring. But if you do your own work, if you make test setups, if you are going to define an experiment, if you're writing software code, think about this. It takes you maybe a couple of hours. What am I making? Why am I doing this? For who am I doing this? It helps. There's other tricks that you can use. And for instance, when you make a very complex system, you do things like breaking down stuff into smaller pieces. So the ASML machine, for instance, is broken down in tens of different pieces. Then those systems are broken down in tens of different subsystems. They're broken down in elements. Some pieces are bought from different suppliers, but it all works. When you all put it together, it works. And you use things like doing a functional breakdown like this. So if you have some kind of part of your system that needs to do a certain function, it has some input, it has some output, and you have some control input that manages this function. It's not always easy to separate input from control input, but there are a couple of tricks that you can use to distinguish those, and it's important to distinguish those. Inputs are sometimes transformed, so a process for making a bicycle out of a piece of metal, the input is metal and the output is a bicycle, so it actually transforms the metal into something else. And the control input is the building plan. Okay, how are you going to make this? But it's not always obvious what is a control input and what is an input, but it helps to separate them a little bit. And here you see an example of a part of an ASML machine, a reticle handler, where you have different types of functionality. And it helps to avoid that you mix up functionality. So there's, for instance, an operator that gives some kind of input to the system. And that operator interface manages this system. So they provide user input, and that's translated into control signals that operate on this system, and this system generates some new control signals that operate on this system, and they have outputs. So this is a payload that's coming in, there's a payload that's coming out, so this could be like a robot that's managing something, and it's all based on the input from the operator. But there's also things like a safety override, so if there's an emergency, that can come in as an input, like a red button. Okay, this is an emergency, then everything needs to stop. And you can break down this function, again, in another function, because this sounded simple, and I made it very abstract. So what is a payload, and what is handling a payload? Well, here it's very abstract, but for this system, it's actually not that abstract. There's actually things coming in, like I'm not going to explain what it is, but a dual pod and a Swift pod and an inner pod and a scan box, and they're all parts that work together and operate together in order to make very clean wafers. And they need to be handled, and there's all kinds of control signals going back. So this is one way. You can also use this for your own system to think, okay, what are the functions that I need to do? This is another view at the same system, but it looks completely different. So here I thought of, okay, what do I need to do and in which order? So it already has some kind of physical structure. So it has here a particle scanner, which is like a black box, but it's a box. And there's a reticle handler, and there's a flow bench where people are working in a clean room. And they want to put in stuff like wafers into this system. And you could do that through two pathways. You can do it through this load port or through this particle scanner. And then you can start drawing things like, okay, how do these wafers and outer pods and inner pods and all these kind of things, how do they flow through this system? So they go from a load port, and in a load port, the box is taken apart, and the inner box is taken out, and the inner box is going to, for instance, a scan box. I think the inner box was going to the exchange port first, going to the exchange box. There, another box is taken out. So in a clean room, you work very clean. So you have boxes in boxes in boxes. So you have an outer box, take it apart. You have an inner box, take it apart. You take out the reticle. And the reticle is going to a scan box where you can scan it, for instance, to see if it's really clean. And then you put it back in the inner box, and then you put it back in the outer box, and then you put it outside. And this was like the first design that we had. Okay, this is very simple, but system engineering helps you here. So I tell you, okay, but I want to sometimes move things from here to here, and then to there, and then to there, and maybe I'm going to add another load port later. Don't know yet, and maybe I'll need another scanner later, a more sophisticated scanner. So it's much better, for instance, to design it like this. We have like, for the robot, one position, where the robot is always going to the same position. It's like a parking position, and can go there to handle an outer pod, can there to handle an inner pod, can go there to handle a scanner, etc. So it's much better to have a nominal position, because if you then add something, then it's just like another standard node that you're going to add. So these are kind of things that you do and use as a system engineer. And then there are other things that you can do, like an activity diagram. This is actually also the same system, and here you see these different pods, like an outer pod and an inner pod. And the inner pod is a base plate, and on the base plate is a wafer or reticle. And you have to take it apart, and you have to put it back together again, and you have to manage it around your system. And you can write down all the activities that take place. It sounds simple. Take out the outer pod, take out the inner pod, etc. But just writing it down, you see all these kind of different functions. And every function is separate. So there's a separate thing doing it. There's separate software code handling it. There are separate and different things that you need to do in case of an emergency. So if things are still encapsulated like this, and there's an emergency, for instance, the vacuum goes away, it's safe, it's not that bad. But if you have a reticle, which is out in the open, and your vacuum goes away in your system, it can be very damaging for your system. So you need to do something else here than what you need to do there. So just writing it down helps. And then from this, you can generate things like, yeah, maybe people know this unified modeling language, maybe for the computer scientist. If you have that first part, you can then write it down. Okay, I have a reticle handler, and I have an operator, and I have a load port, and I can write down this UML diagram that's easy for computer scientists to use. Okay, which type of code do I need, and how do these different types of parts of the code interact with each other? Which things can be done in parallel? Which things do need to be done sequentially, or synchronously, or asynchronously? Still doing fine, I think. 50 minutes, yeah. Almost time for the break. When you've done all the functional analysis, you can make a design for the implementation. So this is not the reticle handler anymore. This, for instance, a car. Very simple. And the car consists of different parts, an engine, transmission. It's not complete, just like a regular example. But you can do this also for your own work. If you design your own systems, break it apart and say, okay, I have a vacuum system, I have a dilution fridge, and maybe I have something else, a control system, and I have a measurement system. Break it up. And you can assign all these different functions to these different things. So it would be very strange if, let's take an example. Yeah, there's part of it is for instance, the payload system, so the luggage part or the seats, etc. for your people. It would be very strange if things like acceleration or braking would be part of your payload system. It has to be part of your engine and your transmission system, etc. So going towards the end of system engineering, another part, of course, is the verification. So if you have done all the functional analysis and you made your system, you need to verify that it actually works. And this is sometimes one of the most difficult things to actually do. Does it actually work as planned? That's why you have to do it as low and early as possible, as we call it. So that means if you made some piece of code, software code, make a simple test, see that actually works, a unit test. If you have larger pieces of code, put them together, write down integration tests or end-to-end tests to see, does it actually work? Because that helps if you then change the code later. You just run the unit test again, or you run the integration test again, and you know that it still works or it doesn't. The same thing for all kinds of measurements. If you do a measurement, you design a system, you expect a certain quality of your vacuum, for instance. Make something that checks the quality of your vacuum over and over again. Not just the first time that you build it and then you start using it. No, measure it every time that you do the measurement. Before you do the measurement, measure the quality of your vacuum. And finally, wrapping it up, there's all kinds of other things that you can do as a system engineer. So I told you already about the risk and opportunity measurement, but you can also do all kinds of trade-offs. So if you design a system, there are many different ways on how you can build stuff. You can build it system A and system B, and they can look completely different, or they can look closely together. But you can make trade-offs like, okay, why is this system better than this system? Maybe it's more expensive, but it can do better things. Maybe this one is a little bit more complex, but it can do more difficult things. So that's a trade-off that you can do. But there's also these things like, for instance, interface management. So this is also an abstract picture. But suppose you have a system that consists of all different kinds of elements. And can be hardware elements or can be software elements, just parts of your system. You can write down relationships between those systems. So for instance, if this is software code, you could say, okay, output from element number 1 is going as input to element 4. Element 2 output is also going to element 4. Output from element 4 is going as input to element 1, etc. Just write down these relationships between the different elements, and you see stuff happening. You see, for instance, that this one is a really critical element. a lot of inputs, a lot of outputs. So that's maybe something where you put special emphasis to. And maybe you have to review this a little bit more than this one. Or maybe you should write more tests to make sure that this one is working because it's a critical element. Here you see some things that are really grouped together. So there's quite some interaction between this part and quite some interaction between this part, but there's hardly any interaction between those two parts. So if you are a system engineer or even a project manager, you can say, okay, let's make this a separate project. And we make this a separate project, and can be different people working on this one because there's not a lot of interaction. But if there's a lot of interaction, you need maybe put all the people working on this in the same team. So you say, okay, there's a lot of interaction in the system. Let's just make sure that all the people are on the same page. With that, I gave you a little bit of insight in what system engineering is. Totally different subject than quantum, I know. But after the break, I want to do a little bit of interaction with all of you and see how can we apply this kind of thinking, these kind of thoughts in designing, for instance, a quantum computer. And that's going to be done after the break, because after 1.5 hours, I think people can use some coffee or tea. So, thank you. In the next part, I have a couple of small assignments, and they're just discussion items. So on a couple of occasions, I ask people to just discuss with each other. For most of the stuff, there's no right or wrong. So it's not like, okay, you have to find the right answer or the most optimum solution. It's more for discussion. It helps you think a little bit and think about various options that you have. And I'm just also very open to hear maybe what people think that's different from how we see things at TNO or TU Delft or in Strasbourg, or maybe new ideas or whatever. So be very open. I'm going to tell a little bit about quantum computing first, to give you a little bit of background for those who are not familiar with quantum computing. And then the case study is thinking about how to build a quantum computer. We're also not going to deep dive, I said that before, not to all of the finer details. It's more like how you do these kind of things. And when you do your own projects with groups of students, I hope this sticks with you a little bit, so that you, when you have group assignments, think a little bit again about, okay, what are we actually making and why are we making it and how are we going to verify it or how are we going to test it, all these kind of things. So it helps you with the thinking process. So a little bit about quantum computing. These are pictures from Quantum Inspire. So like I said, this was developed quite early. So this was the first online quantum computer actually in Europe, I think, where we had two different types of backends. One based on superconducting qubits. We had 5 superconducting transmon qubits online. And we had a system with 2 spin qubits, electron spin qubits. It doesn't sound like a lot, and it isn't a lot, but it's just for demonstrating. And it was also for demonstrating that building a quantum computer is not just about the chip that's over there, but it's the whole infrastructure. It's the control lines, it's the filters, the cryogenic filters, it's the amplifiers, it's the control system, it's the generation of microwave signals, it's microwave hygienity. So how well can you make microwave signals within a certain bandwidth and with certain accuracy? It's about all the software code behind it. Calibrating these kind of systems is a humongous job. You can use a PhD student to do that. Or you can just write lots of software code to automate that calibration, which is also not trivial. So there's a lot of stuff going on in the background. You see this on the outside, where you can build circuits and you can write your own quantum algorithm and you can test it on 2 qubits or 5 qubits. But behind the scenes, a lot of stuff is going on. There's also other stuff that's being built currently. We're connecting Quantum Inspire with supercomputing network in Europe. So we're connecting it now to one of the supercomputers in Amsterdam at SURF. But we're also connecting these backends with a whole network of supercomputers in Europe, the LUMI network, so that people working normally on supercomputers, they can use their own accounts and their own way of working and their own software infrastructure to run hybrid algorithms, both on the supercomputer and on the quantum computer, so they can offload parts of their algorithm to quantum computers. And also that is a lot of software engineering. You need to think about account management and authorization and access, and how are you going to, let's say, make sure that a quantum computer is actually online when the person wants to run their algorithms. And supercomputers are used to run long algorithms, taking days or weeks. Algorithms on a quantum computer take a second. So how are you going to manage that synchronization between a supercomputer running for weeks and a quantum computer running for a second? You don't want the quantum computer to just wait there and do nothing all the time. Or when the supercomputer has calculated for a couple of days, it has to wait for a week because this system is calibrated. So all these kind of things you have to think of. But first, a little bit about a normal computer. Also, this example is to show you that sometimes you really have to go back to the basics to think about what is it actually that I'm going to make. Because a quantum computer sounds difficult, but at a very abstract level, it's very much the same as a normal computer. So you have some kind of memory, which is, in our case, it's qubits, where you store the state of your system. So it's like an in-memory computation, actually. So your system is in some kind of state. This is actually a picture for a normal computer. So we're not into quantum yet, but this is a normal computer. So you have some kind of state. You have some input, which is your program. What you actually do is you run your program and you see, am I ready? So if I'm ready, then I halt. But if I'm not ready, just go back to my program and I execute the next statement. And this is a very simple loop. You just have input, you have your memory, do something, you change the state. Am I ready? No. I look at my program again, do something, change the state. This is actually what a computer does. And this is also what a quantum computer should do. You have some kind of state, you prepare it, you change it, and you see, am I ready or not? And then I generate the output. But in a normal computer, of course, all the operations that you do are based on these kind of building blocks. So you can do an AND gate or a NOT gate or an XOR gate, and you construct all your larger operations from all of these basic operations, and you execute this program, and every time you change the state of your binary register and just operate on them, operate on them, operate on them. So this is how it looks like. Control unit, you execute something, you store it in memory, you look at the result again, am I ready or not? Then I go through this loop. There's something else, an analog computer. Analog computers are already a little bit more closer to a quantum computer, because in a quantum computer you don't have bits, you have qubits. And qubits are not binary, they're continuous. The state of your qubit is somewhere between 0 and 1, or it's on the block sphere for a single qubit, but it's in the Hilbert space for a larger number of qubits. And in analog computers, it's hardly visible there, but there's a, how do you call it, a ruler. When you measure something, it's also not discrete, it's continuous. And in an analog computer, you have signals that are also continuous, with which you do calculations. So it's a little bit closer actually to an analog computer, but I'll stick to the binary computer. And like I said before, it's possible to do all kinds of things with quantum computers, but you cannot do everything. Oh, sorry. So there's certain types of problems that you can do with a quantum computer, and even some problems that are outside the scope of a quantum computer. But in principle, with a quantum computer, you can do everything that you can do with a normal computer. The question is, should you? because it's also very expensive to do certain things with a quantum computer, if a classical computer can do it better. So currently a classical computer can do everything better. So with that argument in mind, you would say, why build a quantum computer at all? Because it's never going to outpass a normal computer, but we hope that a quantum computer will outpass a regular computer. But of course, you're not going to use the quantum computer to do something really simple or something that is not useful to do with a quantum computer. And I'll show the example of the variational quantum algorithms, where you prepare a certain state, you measure it, and then you do some classical optimization to determine the new circuit. You're not going to do the classical optimization on a quantum computer because that's simply not possible at the moment. So you use a classical optimizer in combination with a quantum computer. So in a quantum computer, you have, of course, the bits, which are binary, and you have these Boolean circuits. And on a quantum computer, you have quantum bits, and you have quantum operations, which are more like analog operations, but everybody knows they're not analog, but they're unitary. But it means that you don't have something that looks like this, like a bit register that changes when you do operations on them, but you have probability amplitudes of your state in your system. And continuously, what you actually do with a quantum computer is you do operations, and every time you change the probability amplitude of your system. The thing is, it's a black box. So with a normal computer, every time when you do an operation, you can measure it. See, am I still doing right? Yes, I'm doing right. But you don't change the system. And we all know that with a quantum computer, if you measure the system, it collapses, and it will go from, let's say, a large number of potential states to one of the eigenstates. You can use that for verification, but like I also said, if your algorithm is really complex and your system is in a really complex state, you might have a large number of different probability amplitudes for your whole system. So it's a Hilbert space, so you can have like an almost infinite number of possible states of your system. And if you want to verify whether it's in the correct state, you better not choose an algorithm where the actual outcome is a large number of eigenstates. So normally, a quantum algorithm is written like this, that the goal is to bring it to close to only a few number of states. Few number of eigenstates, very close, not exactly, but at least that when you verify it, there's a big chance that you measure the right outcome. Also for verification algorithms, so make sure that your verification always brings it to one of the eigenstates very closely. So that's the collapse, so you always bring it to one of the states. So in principle, also with a normal computer, you would bring it to one state, but in a classical computer, you have to make sure that you bring it to a quantum state. And you're actually working on all of these states at the same time. You always hear this term, we're working on parallel on a large number of states, but you're actually working on one state. But just when you measure it, you get a random result as output. The thing is, when you go back to the original picture, when you say, okay, I have a computer and I have an input state, and I have an operation that changes the state, and then at the end I measure the outcome, that's true. And in quantum computers, you can do unitary operations on qubits, on multiple qubits at the same time. So you could write it like this. Okay, it's very simple. We have an input state, and we have some kind of large computation that works on many qubits at the same time. And then we measure the output at the end. But the thing is, we can only do operations on single qubits or on 2 qubits. And if you're really lucky, you can do a 3-qubit operation, like maybe some people know the Toffoli gate, which is a controlled not operation. But for most physical implementations of quantum computers, it's not possible to do operations on large numbers of qubits at the same time. There are a few exceptions. For instance, for Rydberg neutral atom systems, you can do something called the Rydberg gate. And the Rydberg gate is actually an operation on a large number of qubits at the same time. but it's just one operation. It's not that you can do every kind of operation that you want. So you always have to break down your computation into smaller steps, single qubit and 2-qubit operations. The bad news is that if you want to break this down, it takes 4 to the power n numbers of operations, single and 2-qubit gates, to do an arbitrary operation like this. So this scales up exponentially. So again, this shows that it's not straightforward to, let's say, break down any computation that you want into something like this. And it's also not always trivial what is the best decomposition of your algorithm for your architecture. So for instance, in our own lab, we have spin qubit systems, which are in a linear array. We now make systems with up to 8 qubits in a linear array. It's not that much. But if you want to do a 2-qubit operation between this qubit and that qubit, it's simply not possible. They're not connected to each other. So you have to write a decomposition in order to make other operations, in order to connect these 2 qubits, for instance, swap operations. So that's why also in these kind of systems you need a compiler. So you need to be able to compile your original algorithm into 1 and 2 qubit gates, but you also have to think about the architecture. So if you have a larger more-to-more end-to-end connection in qubits, you have more options to do the compilation, but if you have a linear array, you don't have that many options. So you have to make smart compilers. So there's also a lot of computer science in quantum information processing thinking about these compilers. It's actually an NP-hard problem. So you need a quantum computer to determine what's the most optimum decomposition for your quantum computer. But hopefully we can find something smarter. There's also a lot of machine learning even going on. People making, for instance, machine learning algorithms to optimize these decompositions from your unitary that you want into your, let's say, thing that you can actually build. These kind of algorithms, BQP, they're bounded error quantum polynomial time algorithms that you can execute on a quantum computer. They're not always correct. So the original definition or the exact definition is that they give the correct answer 2/3 of the times that you execute them. And that's okay for a lot of problems, but it also depends on the type of problem. Oh, it was a little bit too fast. Yeah. So for instance, do you require verification? If you want to know that you are absolutely certain that you have the right answer, then this is not okay. If you want to have 100% guarantee, you usually don't have 100% guarantee that you actually have the right answer with your quantum computer. But sometimes you can do the verification on a classical computer. So you can say, for instance, when you have these code-breaking algorithms, your quantum computer says, well, the answers are 7 and 3. And you can determine that 7 times 3 is 21, so you can do the verification on a classical computer. But if you have a problem like an optimization algorithm, and you say, okay, I want to have the most optimum solution for this very difficult optimization algorithm, and your computer says, well, the answer is 41. You cannot run the same algorithm on your classical computer to verify whether that's really the most optimum value that you have, because it's not possible on a quantum computer. So it's important whether you require verification or not, whether a quantum computer is useful or not for a certain problem. And then there's errors. So a quantum computer will cost you something, and cost is the amount of qubits that you need, and the amount of qubits is the amount of hardware that you need, the number of lines, control equipment, all that kind of stuff. It all costs money, resources, effort to build it, makes it more complex. And a quantum computer is analog, so you turn the knob. It's not like you make a binary switch between 0 and 1. And that means that small errors accumulate. If you turn your qubit 1% off, and you do that 100 times, then you're screwed. So that means, for instance, that this is a really bad error, but if your qubit relaxes from a excited state to a ground state, and you really want to know the exact answer at the end, then you're, I have to be a polite word, then you're messed up. So you need to make sure that errors cannot accumulate, or if they do accumulate, that you have some kind of error correction. But on the other hand, entanglement with the environment and collapse prevents that you can do all types of error correction. So there are some types of error correction that you can do, and some types of error correction that you cannot do. But in the end, it means that when you use error correction, you need more qubits. And you need lots of more qubits. You may need 1,000 times more qubits than for a noisy computer in order to do, let's say, error-corrected quantum computation, which is, again, just costs. And costs here is visualized as euros, but usually it means it's more complex. There are some different flavors of quantum error correction, and I'm not going to explain them how they work, because you can look it up, or maybe you had it in some kind of courses. But for instance, if you have a bit flip error, you can create a couple of duplicates of your initial state, and you just do the calculation on many different duplicates of your state, and you just compare neighbors. You do parity checks between qubits, and if you do parity checks, you can compensate for all kinds of errors in your circuit, as long as you're also aware about how these errors propagate in your circuits, because that's also a little bit less trivial than in a normal computer. In a normal computer, if you have a bit flip, it doesn't affect the other bits. But in a quantum computer, if you have a certain bit flip, it propagates through, for instance, a next gate, a 2-qubit gate, and it will result in an error on this qubit, but it will also result in errors on other qubits. So error correction mechanisms are not always that trivial, and you have to really make sure that you understand how errors propagate through your quantum circuit. The thing is, you don't have binary errors, so you don't have a bit flip or a phase flip. You have small errors, but they're also in 2 dimensions. But fortunately, there are solutions for that, like surface code solutions or color code solutions, where you continuously entangle qubits together. You measure the combined properties of those qubits, do a parity check on those qubits, and with that, in that method, you can encode physical qubit states into logical qubit states of larger numbers of qubits that are entangled. And continuously, by measuring the parity of the qubits, you can detect errors. So you can detect whether there was a bit flip or a phase flip. You actually enforce that. So by doing the measurements, you make sure that, you do it like this. If you have a small error in your qubit, so it's not completely pointing to the North Pole, for instance, if you have a small error, and you do the parity check, it either goes to the North Pole again, or it goes to the South Pole, but at least you know it. So it will collapse to one of those states, and you know to which state, and that's the way how you correct for those errors. But also that correction is not 100%. So there's still a chance that you think it flips to the South Pole, but it doesn't. It flips to the North Pole. So also error correction is not perfect, but at least there is a method to make error correction. So the good news is it's possible. The bad news is that you need maybe 1,000 times the number of qubits, or tens of thousands, or maybe 1,000,000 times the number of qubits that you need for a noisy quantum computer. So this means that for an actual quantum computer, we're not satisfied if we have 100 qubits or 1,000 qubits. We'll probably need millions of qubits to do something useful. Let's do something together. So now it's good that you are in groups, because if you think about a quantum computer and the different building blocks, and you think a little bit about the system engineering approach, okay, how are we going to do this? Then you can already determine, like, okay, which functions can I see, or do I understand that I need for a quantum computer? And just like with a car, you have some primary functions, just things that you need to do quantum computing, and you have some secondary functions, which are might beneficial, you need extra to do with a quantum computer. And you need also all kinds of support. So you need, I'll give away some things. You need a dilution refrigerator, for instance. It's not used to compute the dilution refrigerator, it's used to cool. But if you don't cool quantum chips down to millikelvin level, you cannot do any computation. So it's a support function, it's not a primary function. And then you can think about, okay, how can I implement these functions? But also, which type of people do I need and what are the critical interfaces? So within your groups, I want you to discuss this a little bit and think about, okay, if I were to build a quantum computer, what would be the physical building blocks? And what are different functions that we see? And maybe also, how do I group these together, so these functional groups? So it's just a small exercise, also to get to know your group a little bit. I hope that helps. It says here 5 minutes, but it can take also a little bit longer. I'll look a little bit at the clock. I think there's a question, but I'll just hold it. And just discuss it together. And when we're ready, I just ask every group to just tell 1 or 2 things that maybe popped up. So you don't have to be complete and tell everything, but if one group says, well, we think this is important, and the other group says, well, but maybe we thought this was important, that would help. That's a question. You can maybe start with that. That's your own choice. So go ahead, get to know each other, discuss a little bit, and then after 5 minutes, I'll just go quickly through the groups, just 1 minute per group max, and ask for input. Like I said, there's no right or wrong, but I think one point is hopefully very clear, that depending on the physical implementation that you choose, electron qubits, electron spin qubits, Rydberg atoms, photonic systems, that has an implication on your whole system. It usually has an implication on your primary functions and your secondary functions. But there's also quite some things that you might be able to, let's say, do independently of your chosen architecture. A user interface, for instance, maybe it doesn't really matter whether you're talking with a photonic quantum computer or a superconducting quantum computer. If it's gate-based, for instance, then everything is the same. Then the user interface can be the same. If you're doing measurement-based operations or annealing, then maybe the overall infrastructure for user interface is the same. You still need an IDE or some kind of graphical interface. But behind the scenes, another compiler is used, for instance. But you still have a similar interface to the user. The user still needs to be able to write an algorithm and store the results and retrieve the results, change the name of your results, all that kind of stuff. So this is the first breakdown that we had for the quantum inspired system. I don't know if everything is readable, but this is like functional groups that we made for our system. And here you can see all kinds of different functions in your system. And I'll start with the center one. I don't think it's readable, right? What's in there? It says API Cloud. So this is a software layer that connects, let's say, the outside world, users, through all kinds of other interfaces, an SDK and a web front end and a graphical interface, etc., to quantum computers that are connected to this API. So this is really a critical node where all the communication, classical communication from users to quantum computers is taking place. And the reason why we did this is we say, okay, this is a very generic one, and it doesn't matter whether you have a spin qubit backend or a superconducting qubit backend or a Rydberg atom or transmons or whatever. They can all communicate to this one. And here we do management like user management, account management, sending emails to users. They can store the results and all that kind of thing. So it has some functionality. And then inside the quantum computer, we had a different breakdown. We have like a CPU, we call it. So it's not really a CPU, but it stands for, there we do all the classical processing. So we take an algorithm and we compile it and we turn it into native gates. And from this point on, we calculate the signals, the instructions for our control hardware. In our case, it's room temperature control hardware. And this can be lasers, vector sources, AWGs, measurement equipment, etc. So we group all of this together. And then we say, we have spin qubit system. So we put everything that's cryogenic wiring, cryogenic filters, cryogenic amplifiers, all that kind of stuff. We put in here. because that's a different expertise. And then we have some support systems like tooling and the fridge, etc. So that's a separate system. And the reason why we do this is then you get clearly see the interfaces, what kind of information is going from one layer to the other layer. Is that signals or is that data? So in this case, it's data, it's instructions. So this can be very slow. These are results. Also data can be very slow. But room temperature control electronics generates signals like microwave signals and DC signals and AC signals. So you have different types of requirements here. This is more hardware and this is more software orientated. So that's how we break it down. But if you go to the details, then we have a much larger breakdown of the whole system. And it's not showing all the interfaces anymore, but we break down every system into even smaller systems. And there's a breakdown for almost every system here. There's another breakdown which shows how the software, for instance, the SDK, is broken down into smaller sections, etc. Even up to the level where you have like one piece of control equipment where all of the amplifiers and the filters, etc., that create the microwave signals that we generate, how that's broken down. So this is a totally different expertise, of course, than this one. This one is more the system engineer view, very simple, black box, and then the experts say, okay, but this is how the black box actually looks like. I heard a couple of people talking about different types of qubits. I have another exercise, but first, for the people who are not into it, I'm going to show a number of different types of qubits. I'm not an expert on all types, so I cannot tell you everything about all these different types, but just going to go through it very quickly. So in Delft, we work on electron spin qubits. And this is one example. This is the current chip that we're tuning for Quantum Inspire. It has 6 data qubits, and it has 2 sensing dots on the side. And these sensing dots are used to do charge measurements. So you can measure how many electrons there are in dot 6, in dot 5, maybe in dot 4, but that's a little bit distant, so that's already difficult. So that's why we have a sensing dot on both sides. You can also quickly see that this is very difficult to scale to 10 qubits or 12 qubits because it's impossible to read out the inner dots because your charge sensor cannot sense that far away. So there are issues with scaling this up. And that there's all kinds of gates, barrier gates, plunger gates, and these have these functions. For instance, I don't know, the group over there was talking about exchange interaction. I think it was that group. So you want to be able to control the exchange interaction between qubit 5 and qubit 6. So there's a barrier gate and 2 plunger gates with which you can change the chemical potential of the dots and the barrier between the dots to control the tunneling between the qubits. And those are functions, so you can say, okay, there's a function for B5 to generate a certain voltage, to generate a certain barrier with a certain width and height. And there's requirements for that, because you want to be able to turn the exchange coupling on to do the 2-qubit gate, but you also want to be able to turn them off. So there's a dynamic range requirement for the exchange interaction. It's not just turn it on and off, because on means something, it means a number, and off is not 100% off. There's still some exchange going on, and what do you tolerate, what's acceptable? And if you write down those requirements, then for next iteration, the next generation, you can say, okay, for the next generation, we want this dynamic range to be larger. So that's a way to control, let's say, the engineering. So current state of the art for these systems is we have like 6 qubits, and error rates are like 1% to 4% for 2-qubit gates. There's a lot of other issues. You need to do a lot of tuning by hand. I talked about the readout issue that you have with these type of qubits, but also the speed and the lifetime. It's not that large. They have other types of qubits, like superconducting qubits. So an enharmonic oscillator. Sorry, it takes some time. And for these types of qubits, it's much easier to fabricate them. So they're much larger. So the spin qubits, They're a size like in the nanometer scale. These are more like micrometer scale, so the footprint is like a million times larger than for spin qubits, so it's easier to make them. On the other hand, if you want to scale them to thousands of qubits or millions of qubits, you'll need chips sized like this, or if you want to go to tens of millions of qubits, it's a football field sized chip, so that's impossible to make. But other issues are if you drive these qubits, you quickly derive them to secondary states, so excited states that you don't want to use. So instead of using only these two states, you can drive them to this state or this state. Or you could say, no, I'm going to use this state as well. So I'm able to drive it to this state. So I do not have a qubit, but I have a qtrit, for instance. So it can also make it more powerful. Depends on, again, whether you see it as a bug, as a feature. If you drive it to this state unintentionally, that's noise. And if you drive it to that state intentionally, you can maybe use it. These qubits have a little bit longer lifetime, and the speed is quite well, and the accuracies are higher than for spin qubits. And then there's neutral atoms. I like the movie that was shown there because it looks a little bit like this. You're trying to capture your atoms in an array. And somebody already talked about the Rydberg atom and being able to excite the qubits to the Rydberg state where they have a lot of interaction between qubits. So you can do global operations more easily on these types of qubits. I think this is already outdated. They also have now qubit systems with 1,000 qubits or even 600 qubits or something like that, or 1,200, I don't remember exactly. They have also quite high fidelities. And you can move the qubits around in this array, which is very nice. You can actually swap the positions of qubits. There's a famous picture where they put an array of qubits in the shape of the Eiffel Tower. That's good for French calculations, but not if you want to do a German calculation. But it's nice that you can do these kind of things. So there's other things that you can do with these types of qubits that you can do with transmons and spin qubits. But you also need lasers. That's a little bit more difficult to encapsulate all the lasers in the right position and to be able to control all the qubits at once. And for the readout, you need indeed CCD cameras. And you need high photon collection efficiency for those cameras, because if you miss a photon, then you're actually not reading out the qubit, or at least you are reading out the qubit, but you're not collecting the data. And they have long lifetimes, the Rydberg state, so this is also a nice option. And I wanted to show trapped ion, but I know the most little about this one. But for trapped ions, they have very high fidelities for 2-qubit gates. I think they're a world record holder for 2-qubit gates, so that's very good about these systems. They have a very long lifetime as well. A lot of work is done in the US on trapped ions. But they have these things where you get some oscillating modes between the different ions, which might be very difficult to control if you go to larger numbers of qubits in the end. It's time for another discussion to keep you fresh and awake. It's a long morning. So I did this when I didn't know there were groups. So this is still in your group. Don't with a person with left and right. Just within your group. Discuss which qubit technology you would choose and why. And you can change, maybe, if you picked electron spin qubits, maybe it's good to pick another type and discuss that a little bit more. And see if you can determine some special functions that are special for this qubit. And also, what elements do you need to control this qubit? And it would be nice to think just about something that you don't have experience with, just as an exercise. So also, again, a few minutes in your groups. I'll do this a little bit shorter because of time, and then I'll do a quick round and a little bit faster than last time. Okay, yeah. So known technology is also very handy. Yeah, that's true. So I think that also holds for everything here. So I don't know a lot about ion traps, but for instance, for spin qubits, we as TNO made a choice to focus a lot on spin qubits, for instance, electron spin qubits, because that's made with silicon, and a lot of it is based on standard transistor technology. It's not completely identical. but at least it means that when there is a breakthrough there, you can use, for instance, standard foundries that are already used to making normal transistors. You can use that same infrastructure to make quantum dots and electron spin qubits, or Hall spin qubits for that matter. And there's a lot of research already done in that field to make really good gates and good control electronics and those kind of things. Approaching a little bit the end, so talked a little bit about the qubit and about the requirements on qubits, and I wanted to show you a little bit more detail on one specific type, quantum dots, not because I want to highlight this one, but simply I know a little bit about this one, so I can tell a little bit about this one, but also to show you that there's large systems, the whole quantum computer, and you can group it down into smaller parts like the control electronics and the chip, etc. But that's not the whole story. You can go deeper and deeper and deeper, and everything is almost a system on its own. So you can approach it at the same way as you do for large systems. So for a large system, you can say, okay, what is the function of a quantum computer? It needs to compute, it needs to spit out results, it needs to have a user interface, etc. But if you look at the chip, there's all kinds of functionality on the chip as well. So this is for a standard transistor. Sorry, this is not for, I removed those slides. So this is for a quantum dot system. You have gates, and those gates have functions. And for instance, you want to be able to change the potential difference, the barrier between the gate and the drain, in order to load or unload electrons into your quantum dots. And you want to be able to, in the end, have single electrons in your quantum dots. Or sometimes, if you want to go to different states, 3 electrons or 4 electrons. If you want to make exchange-only qubits, for instance. But there's a function for this voltage to do something. You want to move an electron from one position to the other position, and you want to do that move, for instance, coherently. So if you want to do tunneling from one dot to the other dot, and you want to use that as a function, you better be damn sure that you can do that coherently and identical all the time that you do it, that there's no difference between the times that you do that operation. And if you look at the device in more detail, you see all of these gates here, and they all have different functions. So this one is here to accumulate electrons in the sensing dot. These are the plunger gates. They're used to also accumulate the electrons in that location, but also to change the chemical potential of these dots. So you can increase or decrease the potential in those dots and put, for instance, excited spin states or ground spin states at the same level as your drain or your source, or to control the exchange coupling between those two dots. So you can actually see functions of all these different gates, and sometimes these functions are mixed. Accumulating electrons is something else than turning on or turning off the exchange energy. And it's good to always separate functionality as much as possible. I'm going to skip this a little bit of time. This was explaining, well, I do explain because you use it for the last exercise. So in spin qubits, do it very fast. You have the spin state of your electron, and spin states are actually degenerate. So spin up has the same energy as spin down state if you put a single electron in a quantum dot. But if you apply a strong magnetic field to it, then one of these spin states gets a higher energy than the other spin state. It depends on your material, whether spin up or spin down has the highest energy. But for instance, in silicon, spin up has the highest energy and spin down has the lower energy. And these two levels are the two levels that you use to encode your qubit in. So a 0 state and a 1 state. But what also happens when you put electron in a magnetic field like this, they start to precess. So this qubit state, it actually goes around and around and around at a certain frequency. It's called the Larmor frequency. And that's okay if you read out the qubit, because if you read out the qubit, you collapse it onto the z-axis. So it doesn't really matter that it's rotating around the z-axis, because it doesn't matter where it is in that position, as long as you do readout. But if you are controlling this qubit, it's really a nuisance, because we do not want to be able to only rotate the qubit around this axis, which is then naturally done by itself. But we also want to be able to control, for instance, rotation around the x-axis. And how do we do that? We generate microwave signals that we send to this qubit to control the rotation. And for that, we also need an extra magnet. I'll show you that a little bit later. So suppose that we have this Larmor precession, and it's at a certain frequency. And we turn that reference frame, and we start to rotate with that reference frame together with the qubit. Then actually it looks like this qubit is standing still. There's a magnetic field over there, and if we want to apply a magnetic field over here to start rotating like this, then we get another precession around this axis. So we can make the qubit rotate around the z-axis, which is a natural rotation, and we can make it rotate around this axis, but then we need to make a static field in a rotating reference frame. So it's actually a rotating field, it's an oscillating field. And how do we make that oscillating field? We do that with a special micromagnet. So we put a micromagnet on top of this system, which has a function, namely to create a gradient in the magnetic field. Oh, sorry. So we have the external field, and there's a gradient in this direction, and there's also a gradient in that direction, and the gradient in that direction is used to address different qubits. So this qubit has a different total field than this qubit, and if the total field is different, then the resonance frequency is different, and this way we can address this qubit with a microwave of a certain frequency and this qubit with a microwave of another frequency. If we then determine the Larmor frequencies of these qubits, we can drive it with a microwave pulse, which has an envelope, and this envelope determines the amount of rotation around the x-axis. So you can rotate it over pi or pi over 2 or a fraction of pi. The phase of the pulse determines whether it's rotating around the x-axis or the y-axis or any axis in the xy plane. And the pulse area, so not only the envelope, but the pulse area determines the total amount of rotation. Very fast, just because of time. If you want to learn it a little bit better, talk with me after the break. But I want to show you this. So we have the full system, a fridge. Inside there's all kinds of cooling equipment with all kinds of temperature levels. Then we have a cold finger on which we have a PCB put, and on that PCB you have the chip, and everything is a system. So this is a system by itself with all kinds of functions. You need to be able to send microwave signals to the chip. Here you have the chip bonded to the fridge. But if you zoom in a little bit deeper, and sorry, it's blurred on purpose because there's some confidential information on how the design is made, so I'm not going to show you the complete design. But you can imagine that you have all kinds of gates coming from the edges of the chip. So this is still centimeters large, going to the center, and in the center you have all these gates coming together, and they all have their own functions. So plunger gates, barrier gates, plunger gates, barrier gates, screening dot gates, sensing dot screening gates, and sensing dot gates. And if you zoom in further again, closer to where the dots are, then all these dimensions have specific requirements on them. So you don't want them to be 12 nanometers wide or 20 nanometers wide. You want to be them 18.5 nanometers wide, because otherwise the exchange interaction becomes too large, for instance. Or the distance between the sensing dot and the dots should be of a certain value in order to have a high sensitivity. So everything is a system and everything has their own requirements, even up to the sensing dot. And there I want to finalize with the last assignment, and then we can go for lunch. So we'll do this also quickly. Don't do it in groups. Takes a little bit too long, I think. I'll take a shortcut here. Very quickly, just raise your hand. What kind of functions do you quickly see here in this design? What's the function of this one?
Manipulation and readout.
Oh, yeah. And how do you see the readout? Yeah, that's right. You manipulate them using the DSL? Yeah, in this case, we use indeed a microwave signal that's being sent to one of these gates. Yeah, yeah. And I'll skip the other one. What do you think in this function is the most critical one? And I'll tell you a couple of functions. So this sensing dot has the function to read out the quantum dots. The quantum dot have a function to store an electron and keep it in a certain position. The plunger gates have a function to change the chemical potential. The barrier gates have a function to change the exchange interaction. What do you think is a very critical one in this sense? Trapping the charge, yeah. It is an important one, but for us, we consider it not as the most critical one. That's right, but if you don't have readout, then you also don't have qubit. Readout? Or somebody else? Gates, yeah. Yeah, it's always a combination. But I'll just explain what we currently consider as the most important one, and I'll explain you why. It might not be the reason that you thought of. Readout, function readout, is currently for us the most critical one. The reason is it takes us about half a year to manually tune this device to a level where we can automatically calibrate it. So first we need to tune it, and then we need to automatically calibrate it. To tune it, we need to do lots of measurements every day. Measurements. To automatically calibrate it, we need to do a lot of calibrations. So in order to keep it online for an hour, we need to do 15 minutes of calibration. If we can decrease the readout time with a factor of 10, everything is easier and everything takes a lot less time, and that's simply money. So for us, it's simply the costs of developing such a system and tuning it and throwing away all kinds of devices that do not work. We can do that much faster if we can do the readout faster. So that's the most critical one for us. And I'm saying there's not a right or wrong here, so every answer is good. But for us currently, that's the most critical one. We know how to store electrons. We know how to manipulate them a little bit. We know how to do readout, but we want to make that faster and faster and faster. Finally, skip these ones. I'm at the end. Want to do only one question because of time. And that's an ELSA question. So ethical, legal, societal question. Quantum computers, quantum communication systems, quantum sensors can be used for all kinds of stuff. Just want to have some people maybe thinking about this and think, do you think quantum is good or do you think quantum is bad for society?